chapter, I think, which should be up there as well. So we've been talking here about gases, and we talked about obviously some gas laws last time. We talked about the idea of partial pressures. We saw some different sort of partial pressure problems. Um, Ones where you can basically just use sort of the ideal gas law and basically calculate the pressure for each of the gases that are in a mixture. Remember that since they are basically in the same container, both the temperature is the same for all the gases, the volume is the same for all the gases. So essentially, when we have that sort of situation and we're using the ideal gas law, really the only thing that's going to be different is the moles of each gas. So once you have that, you pretty much can solve for pressure out of the ideal gas law. Again, for each gas sort of separately, and add them all together, and then you'll have your overall or total pressure of that mixture. We also saw that a lot of times gases are collected sort of over water or saturated with water vapor. That's another sort of partial pressure situation. And in that particular case, usually what happens is we actually do collect some gas in terms of steam or vapor. And we're not really interested in the water part of that. So we do have to subtract it off. So usually we need to take the total pressure minus the vapor pressure of water at a given temperature. And that will give us the partial pressure of the gas we're really interested in a collection like that. And lastly, we saw that sometimes we don't really have enough information, for example, temperatures or volumes, to calculate the pressures using the ideal gas law, but we might have enough information to figure out the moles of each gas. And in that particular case, we could use the partial pressure of a gas is equal to the mole fraction of the gas times the total pressure. So again, that's a useful sort of little formula there. Allows you to sort of calculate partial pressures, total pressures. Again, if you really don't have necessarily enough information to really go into your ideal gas law. We finished up talking about sort of kinetic molecular theory of gases, and two really parts of that sort of theory is really what makes something an ideal gas that we've been talking about. And the two parts of it is that the volume of the gas itself is relatively small compared to the container or the volume of the container in which it's in. So we assume that the actual gas molecules themselves have no volume or the volume zero. And that's what pretty much makes something sort of an ideal gas. The other sort of part of the kinetic molecular theory that we assume is that there is no attractive forces or repulsive type forces between different gas molecules under normal sort of conditions. And that really is why, when we were talking about partial pressures, that even though there are many different gases perhaps in a container, we could kind of do the calculations separate for each gas and assume that really one gas will have no effect on another, even though they're in the same container. Again, that's part of what makes something sort of an ideal gas or an ideal gas situation. Any questions on any of that stuff we talked about last time, I think? Okay, so I think this is about where we left off. So the next thing we're going to really talk about is sort of the speed at which gases sort of travel, or the velocity at which gases really travel. So if we look at, for example, here in the first graph, we have the same gas, which is nitrogen in this case. And we have nitrogen gas at some different temperatures. And what we can see here, if we look at this, is at different temperatures. As the temperature changes, the actual speed of the gas will also change as well. So as we go from, say, 100 to 300 to 700 there, this is the speed right here in meters per second on the bottom, or the velocity. And we do see that at like 100 Kelvin, pretty much a majority of everybody has this speed right here. It gets faster as we go to 300 Kelvin, gets even faster in terms of proportional speed, in terms of what it is at, say, 700 Kelvin. If we draw some straight lines, unlike that, you'll have the velocity there for each of them. So what we see is what we sort of would expect as we increase the temperature. The gas molecules is obviously going to gain a lot more energy. As they gain a lot more energy, they're going to start flying around a lot faster. Also would result obviously in more collisions you would expect if the volume doesn't adjust or anything like that. Now, if we look at sort of what happens if we look at different gases, though, at the same temperature. So here we have some different gases, but they're all here at the same temperature. So we got Cl2, and the speed's about here. N2, the speed's about there. And He, or helium, I guess they call that, is right about there, is the speed. And what we see is when we look at sort of the same temperature for each of these gases, we do see that the speed does increase with actually decreasing molar mass. So we see that our lightest sort of gas molecule is traveling a lot faster than our heaviest gas molecule in this case of these three, which is here, heaviest, and our lightest over here. And there actually is a way that we could calculate the velocity of a gas molecule, and that is what is sometimes referred to as RMS. RMS stands for the root mean square RMS velocity. So the root mean square velocity is usually in meters per second, and that is basically the speed at which obviously our gas molecules are traveling. And this is the formula here. It is the square root of 3. And the R value here is actually not the R value that is used in the ideal gas law. It's actually the R value that is used with energy, which is 8.314 joules per Kelvin per mole. So this R in this formula here is actually this version of the gas constant. T is our temperature, and it is in Kelvin like pretty much everything else. This M here is our molar mass. And when we use this particular equation to make sure that everything sort of comes out correct, we do want to do our molar mass a little bit different than we normally do. So normally we do molar mass in grams per mole, but it actually needs to be in this formula kilograms per mole. And it does need to be kilograms per mole in this particular formula. And the reason for that is actually from R and the joule. There is a relationship that a joule is equal to a kilogram times a meter squared second squared. So that is what a joule equals. And what that does, if you get everybody in that right sort of formula, what you'll end up with, get somewhere to write. If we just look at the units here, so if we do our square root here, our R, which is joules per Kelvin per mole, would end up being kilograms meters squared second squared Kelvin and mole. Again, that is a joule, and that's from R. Our temperature would be in Kelvin, and our molar mass is why we want it in kilograms per mole. That way, when we look at the units, the kilograms will cancel, the moles will cancel, the Kelvin will cancel, and what we're left with is the square root of meters squared over second squared, so that when you're all said and done, you end up with units of meters per second. The good news is changing those units to kilograms, meters squared, second squared doesn't change the value of R, which is a constant. Really, the only thing you really have to worry about in terms of units is that molar mass. You got to make sure, again, it's in kilograms. So all of the units cancel out correctly. Any questions on that there? So why don't we try one here? Let's take a look at, why don't we calculate the root mean square velocity for helium, which is 4.003 grams per mole. And we'll do neon, which is 2018 grams per mole at 25 degrees Celsius. And again, here R is the 8.314. So take a couple of minutes here, calculate both of them, and let's see what you come up with. I'll do it as well if I find my calculator.
Hey, Professor Efron,
Yeah.
could you go back to the graphs? They didn't really make sense to me, and I was hoping I can get some clarification on it.
Yeah.
So I don't quite understand the y-axis. It's the number of molecules. So is that saying as the number of molecules go up, the molecular speed at 100 degrees Kelvin is topping out at say like 250 or whatever, and then leveling out as you take them away at the same temperature?
Yeah. So basically, what this graph is sort of showing is again, say this first one has 100 Kelvin. At 100 Kelvin, there's a certain proportion of molecules that will sort of reach their top speed, if you will, right about here. So that's the proportional molecules that basically have hit the highest sort of speed at that point. Is at the very top of the curve. Um, and that would represent, this speed here. When we increase the temperature, we actually get a little bit wider margin of guys that can kind of reach that sort of top speed. But on average, the top speed would be sort of at the peak of it for those guys. And same thing here when we get to even sort of a higher temperature, we obviously get a lot more molecules sort of involved, sort of a wider proportion of speeds, but these guys will reach sort of the top speed right about here. In terms of proportion of molecules, we do actually see sort of the number of molecules that are reaching that top speed is actually getting smaller as you go down with temperature or increasing temperature. Over this, and that's because you just have a lot more gas molecules moving around. So you're going to have a more wide variety of speeds sort of happening at that temperature. So people are going to be sort of at different speeds as they're sort of moving around. But there's a good in terms of the top speed is sort of at the peak in all these guys. Same thing over here. Um, as we keep the same temperature, when we sort of decrease the molar mass, we're going to get sort of a wider variety of guys able to reach a little bit higher speeds than you would even at this point and stuff like that. So I kind of have a couple of things going on here, but basically for the purposes of this, we're just looking at sort of the peak of that graph or that hill, and that's really where at that particular temperature or that molar mass, that's basically the top speed that those guys can kind of reach at that point. And like anything else, right, if we're all running, right, there's somebody that's going to be kind of the fastest, right, but there's some that might be right on their tail or a little bit slower and stuff like that. So as the temperatures sort of change and more mass changing, they're ramping up, but sort of the maximum sort of speed that they can hit is that peak of that hill.
The root mean square isn't the top speed, it's just the average. I'm sorry, you muted.
I did mute myself. I thought I was done talking. I'm sorry. But yeah, so like a mean, so kind of like an average, right? So it's kind of like the average sort of high speed that, we would expect these guys to be flying around, or sort of the top speed, if you want to think about it on average, that they could reach under those sort of conditions, be the temperature or molar mass that they're at.
Thank you.
Yep. Okay, so let's take a look at calculating these two guys here and see what we end up with. All right, so we are going to be looking for the root mean square velocity, which is sometimes abbreviated with this little symbol here. And it is the square root of 3RT over the molar mass. So if we do it we'll do it for helium first. So it's going to be the square root of 3, again, our R here, the 8.314. And it really is joules per Kelvin per mole. But again, if we kind of substitute for joules, the kilograms, meters squared, second squared, again, we can kind of see the units that we need. We do need to convert our temperature into Kelvin. So that's going to be 298 Kelvin on that. All divided by our molar mass. Again, because really this is kilograms up on top, we need to really take our molar mass and divide it by 1,000, and that should get us something like 0.004003 kilograms per mole. As I mentioned before, moles will cancel, Kelvin will cancel, kilograms will cancel, and again, that's going to leave us meter squared over second squared, which we're obviously going to take the square root of, and that will leave us with meters per second. And if we do all that good stuff there, a little square root action perhaps, We'll call it 1363 meters per second. In terms of how fast on average our helium guys are flying around at 25 degrees Celsius. So if we do the same calculation here for our neon, pretty much going to be same exact numbers. The only difference is again going to be our molar mass. So we'll put our guys in there. And again, just like we did before, we want to make sure we get this into kilograms so that everything cancels out correctly. And again, we divide it by 1,000 basically to do that. 0.02018, I think, kilograms per mole. Again, everybody going to cancel out just like last time, except for our meters and our seconds. And if we do that for that one there, we'll call it 607 meters per second. First off, any question on that particular calculation there?
So, okay, so this is what I did. I didn't know if this is against the rules or not, but it made it easier. I just made R be 8,314, and then you can keep the molar mass the same.
Yeah, I mean, at some point you got to do some conversions, so I guess that will work out okay. I suppose you have to take that 1,000 sort of factor into consideration, basically. So I think it will work. I'm not 100% sure, but so I'll give you a 90% guarantee on that. Then maybe it'll be all right in that sense. Other questions on that? So this is actually the problem that we sort of did earlier. If you remember, we went back and kind of looked at our partial pressure problem that we did earlier. And if you remember, we did the partial pressure of these two guys in sort of a mixture. And if you remember, we did see that helium supplies something like, in that particular problem, like 12.1 atmospheres of pressure, while this guy, I don't remember what it was, like 2 point something atmospheres. And this is really why, again, that happened in that sort of problem. We see that neon, which is heavier, is traveling at 607 meters per second, which is about 1,700 miles per hour, while our guy up here is about 1,363 meters per second, our helium, which is much lighter, traveling much faster, about 2 times faster, about 3,000 or so miles per hour. And obviously, because it's traveling a lot faster, our helium, because it's lighter, is going to cause more collisions, and we would expect, like we saw in that partial pressure problem, to be sort of the major contributor in terms of the pressure. Any questions on that there? Okay. So root mean square velocity, as we talked about, again, is a way you can sort of, on average, based on your temperature or mass, sort of get an idea as how fast your gas molecules are basically traveling. Another sort of property of gases is what's known as gas diffusion. And gas diffusion is the gradual sort of mixing of one gas molecule with another by virtue of their sort of kinetic properties. So what we see here is a couple of things. We see a bottle of ammonia, basically, which is going to make ammonia gas. And we see a bottle of hydrogen chloride, hydrochloric acid, which is going to make some hydrogen chloride gas. And when these guys come together, basically our NH3 plus our HCl, it makes some ammonium chloride, which would be this white stuff that we see here. And what we see when we open these two bottles is we see the mixing of those two things is actually occurring over here, closer to this guy. And the reason for that is kind of what we just talked about in terms of the masses of these guys. We have our HCl, which is 36 grams per mole, and we have our NH3, which is 17 grams per mole. So we would expect that the NH3 should be traveling a lot faster than our slower moving HCl. So what that means is because our NH3 is traveling a lot faster, it's going to find its way over to the other side. As our HCl comes out of the bucket here, it's going to be moving slower. And that's why we kind of see the mixing occurring over here closer to the slower moving HCl molecules. And we can actually calculate things like rate, and that's what we see here in this equation here to calculate some of this gas diffusion. R1 and R2 is the rate, so the rate under different sort of circumstances. And M1 and M2 here, again, are our molar masses. And this guy, we can leave in grams per mole, so we're all good in our normal sort of units for molar mass in this particular case. So we do see that ammonium chloride mixing closer to the slower moving gas molecules. And we do see obviously the faster moving NH3 being able to sort of carry itself over there a lot faster. Another sort of aspect of sort of gases is what's known as gas effusion. And gas effusion is really the process where we have a gas that's under a pressure sort of escapes from one compartment to the next. You got like a little hole right about there. So at some point, these gas molecules will sort of pop over to the other side in this situation. And we have pretty much the same formula that we just saw, where we have R1 over R2 equals T2 over T1. And these are time. So these are two different times, basically. So time 1, time 2, our rate 1, rate 2, and our same guys over here are molar masses as well. So we can use this formula to help us sort of understand or figure out certain things if we know how fast, say, another gas sort of goes through a fusion. So let's take a look at sort of the problem that we have on the bottom here and see how we could kind of go about working it. And we have nickel forms a gas compound with the formula NiCOX. We want to really figure out what is the value of X here. If we know that under the same conditions, methane, which is CH4, basically can fuse through the hole, if you will, about 3.3 times faster than the compound that we're looking for. So I'm just going to come back. I think I got a page of somewhere I could write right there, I think. So we're really looking for really what is this formula here in this particular problem. We know that R1, if we call it, we know that basically methane will be 3.3 times faster than R2 if R2 is our compound. We know that the molar mass of CH4, so we'll call CH4 all of our ones, if you will. So 12.01 plus 4 times 1.008. And we could calculate our molar mass of methane. Got something like 1604 grams per mole. So that would be our M1. You could call it M2 if you want, but I'm going to call it M1. And again, that's why my R1 is 3.3 times faster than R2, which is my unknown, basically. Right? And again, you could flip it around if you want, as long as you keep, obviously, those guys that are together in the right spot. So we'll use our little formula there, which is R1, R2 is equal to the square root of M2 and M1. So we know that R1 is 3.3 times faster than R2. So that gives us 3.3 R2 divided by R2 equals the square root of my M2. And remember, my M1 is my methane's molar mass. So I'm going to put that in there. This makes the math on this side pretty easy. These guys are going to cancel out, so I don't really even need to know what those values are, but that's going to give me 3.3 is equal to the square root of M2 over 16.04 grams per mole. Obviously, to get rid of the square root, I need to square both sides. So I'm going to take 3.3 and square it. That's going to give me 1089 equals M2 divided by 16.04 grams per mole I'm going to multiply the 16.04 to the other side, and that will give me that the molar mass of my unknown compound would be, call it about 174.7, we'll call it 174.7 grams per mole. First off, any questions on this part of the calculation? Again, we're doing this to figure out what the molar mass of our unknown compound is based on a fusion sort of information. So we still need to actually figure out what the question is asking for. And the question is really asking for kind of like, what is X, right? So in this particular formula, we're really looking for what is X. The one thing that we do know for sure is there is only one nickel, right, in this particular formula. And we know that the molar mass of nickel, if we go to the periodic table, I can see it is 5869. So we know that out of 174.7 grams per mole, 50, what did I just say there? Is it 5869, I think? 5869 grams per mole is nickel, if I saw the number right, hopefully. So what we got left, if we subtract that off from the molar mass, is we got about, we'll call it about 116 grams per mole left. So what do we know is left? What is left is we have a carbon and oxygen units, and we have so many of those carbon and oxygen units. So the one thing that we know about carbon and oxygen is carbon is 12.01 and oxygen is 16. And that molar mass there, which is 16 plus 12.01, is 2801. That represents the molar mass of every carbon oxygen unit, basically, that we have. And that's essentially what we got going on here is carbon and oxygen. So the remaining 116 grams is made up of that, so many of these 28.01 units. So to figure it out, we could basically just take 116 divided by 2801. And roughly speaking, we will get, we'll get the calculator to shut off. Maybe it'll come back. There you go. Roughly speaking, here we will get about 4.14, which roughly means there's about 4 of those units present. And that means that the actual formula here would be nickel, CO, and 4. Any questions on how we went from the molar mass of the compound to basically our X? Our questions on a fusion or diffusion? Okay, so the last thing we're going to talk about in terms of gases is we're going to talk about sort of what's referred to as real gases, not those fake ideal gases we've been talking about. So we're going to talk about those real gases here. So as we talked about, under ideal conditions, if you remember, basically from the kinetic molecular theory of gases, like we talked about at the beginning today as well, we assume that the volume of the gas molecule itself is negligible or zero. And we also assume that there is no attractive forces or repulsive forces that occur between different gas molecules. And in an ideal situation, if we solve for the ideal gas law for N, we should end up with a ratio of 1 in a pretty ideal situation. And what happens though when we're not in an ideal situation, we're in a situation which are sometimes referred to as a real gas situation or real gases. And those occur at really low temperatures and really high pressures. And the reason we don't take into account those things like volume or sort of attractive and repulsive forces is under sort of normal conditions, it's not really a big deal. There's not a lot of interaction sort of happening. But if we think about what happens when we have really high pressures, right? If you just think about, say, something like Boyle's law, have a really high pressure, that usually would mean your volume is fairly low. which means if you got all these gas molecules in this very, very super small area, a couple of things do come into account that you do have to take obviously into account. One of them being, as you can see in my really badly drawn picture there, that my little circles, which represent the gas molecules, their actual volume is actually important compared to the overall volume of the container they're in. It's pretty relevant in that case. In addition, pretty much everybody is slammed together, which means they are definitely going to be near each other. They're definitely going to come in contact with each other. And you do have to take into account things like their interactions with one another, the repulsive forces, the attractive forces. Same thing happens when we actually drop the temperature really low, right? So if we drop the temperature really low, same idea. We have these gas molecules. They're now moving a lot slower, right? Because the temperature is a lot lower, which means as they go to sort of pass each other, they're definitely going to be in the presence of each other for a longer period of time, which means, again, they're going to be interacting with each other a lot more than they would under normal conditions or ideal conditions. So when we deal with real gases, we cannot just assume that there is no attractive forces, repulsive forces between different gas molecules, or that the volume of the gas itself is not important. Because again, under these extreme sort of conditions, if you will, those things are definitely really important. The reason why we don't really have to worry most of the time when we're dealing with gases, and we sort of often will assume sort of ideal conditions, is when we look at this graph, we really start to see some deviations for these different gas molecules, as we start moving pressures, right? So out here is like 200 atmospheres, 400 atmospheres, 600 atmospheres. And we see a lot of deviation from ideal conditions here. But if you think about when we think about what normal sort of pressure is, it's about 1 atmosphere, which is like way back over here. And you can see that, even at that very small pressure or normal pressure, there's not a tremendous amount of deviation from ideal conditions. So we could usually assume, everything's sort of ideal. But you can see as we move out in terms of pressure, we get some pretty big deviations happening from sort of the ideal condition. And that's really why under normal conditions or most conditions, we do assume that sort of ideal situation and we don't have to really worry about it. But again, if you have really high pressure or low temperatures, you do have to take those into account. So as I mentioned before, it really is those two things from the kinetic molecular theory that we do take into account. And again, we do have to assume that, there is going to be some attractive forces or repulsive forces that we don't in an ideal situation. And again, the volume of the gas itself is going to be significant compared to sort of its normal ideal situation. And again, at low temperatures and high pressures, this is really where that sort of kicks in. So, because real molecules do take up, excuse me, because real molecules do take up space, their molar volume is larger than we would be predicted under an ideal situation. So, when we're talking about molar volume, that's our 22.414 liters per mole, right? And we do see argon and we do see an ideal gas. And we see that in terms of pressure, under sort of reasonable pressure, sort of high pressure, both of those guys are pretty close to each other. But really, as we start building out the pressure here, we do start to see some deviation here between the ideal situation and sort of the non-ideal situation. And in terms of the molar volume, we see that it is actually going to be a little bit larger than it is in the ideal situation, thus taking up more space, and we do have to take it into account. So the effect of molar volume was sort of looked at by our good friend van der Waals. And basically what he did was he sort of took the ideal gas law and made some correction values to it. And they're sometimes referred to as van der Waals constants, and they're A and B. And these are van der Waals constants. And you do actually typically look these up on a table. So you typically do look up on a table. And it is specific for different gases. So it is specific for different gases. So you would actually look it up, for example, say for CO2 and find the van der Waals constants for CO2, which would be different than, say, for methane or something like that. And basically, van der Waal built in sort of a correction factor for the difference that occurs in the molar volume here. Here's pretty much our ideal gas law. This is our moles times this correction factor for volume. And again, we're going to add it to sort of the volume component of the ideal gas law. Again, a way to sort of correct for that additional volume that we do have to sort of take into account in a real gas situation. Now, when we look at real gases under low temperatures, we again do start to see some deviation from ideal behavior. As I was mentioning before, at those low temperatures, they are definitely moving a lot slower. They're going to be in contact with each other for a longer period of time, and that is going to make some attractive forces and repulsive type forces really come into play. And we see that here again as the temperature really starts to come down. We do start to see some deviation here between an ideal gas and sort of a real gas in terms of its pressure. So obviously, when we start to get some of those interactions happening, we actually start to see a little bit lower of a pressure in that real gas situation, because again, you got some drag perhaps happening. So if you have this gas molecule that's not attracted to anybody, just flying around, it's again free to pretty much hit the wall. But if you have this gas molecule that's flying around, but then is attracted to another gas molecule behind it, it's kind of going to be pulling it back. It's going to cause maybe the collision to be a little bit less and not as often. And we would see a slight deviation in terms of the pressure we would expect in an ideal situation versus a real gas situation. So van der Waals also came up with sort of a correction factor for the effect on pressure that's caused by the attractive forces and even really the repulsive type forces that occur in this situation. And again, this is our ideal gas law here, solving for P. And we're going to subtract off sort of this correction value. And A is our van der Waals constant, again, specific for a specific gas. And again, it creates sort of an adjustment that we do to the ideal gas law. And just to sort of illustrate that, as we was talking about, again, in the absence of any type of attractive forces or repulsive forces, this gas molecule is free just to bang into the wall and move on. Again, as he starts to go towards the wall in a real gas situation, he is going to get a lot of drag from that attractive forces from the other gas molecules. Again, that's going to affect obviously the collisions. It's going to affect the pressure that's going to happen as well. So taking both of these sort of correction values that was built in by van der Waals, we get what is sometimes referred to as the van der Waals equation for a real gas. And it is a scary looking equation, basically, version of the ideal gas law. It really is the ideal gas law, but it has those two sort of correction values built in, one to correct the pressure associated with the intermolecular forces, one to correct for the volume associated by the volume of the gas. Everybody here is still the same stuff that we use in the ideal gas law. So P is still atmospheres is usually what you want it in. A is our van der Waals constant. N is still our moles. V is our liters. This is obviously our liters as well, our moles, our other van der Waals constant, and our normal N and our 0.08206 version, and our temperature in Kelvin. So as you can see here from the table, different gases will have different values for A and B. So if you ever have to look them up, you definitely want to make sure you're looking it up for the correct gas so that you get the correct ones. I would also very much caution you that depending on where you look it up, these units may not always be perfect to go into, say, van der Waals equation. You may have to do some other conversions as well. So sometimes textbooks typically will give it to you in sort of in the right units, but if you look it up in some other manual that you may have or whatever are fine. Sometimes the units are different, so you do where we want to watch this. So first off, any questions on van der Waals equation? Obviously, you would solve for anything in there like you normally would. A little bit more math, obviously, involved in it. So, why do we typically use sort of the ideal gas in most of the situations that we do? Well, really, as we saw earlier, we are usually dealing around 1 atmosphere, and there's not a lot of deviation that occurs, from the sort of ideal behavior at 1 atmosphere. And really, the ideal gas law is more of a generic sort of formula. We could use it for any gas we want. We don't have to look up any type of constants. The van der Waals equation for real gases is really a lot more specific type of gas law, where if I wanted to use it for CO2, I would have to go find the values. But then if I want to use it for H2, I got to go find some different values for A and B. Well, if I want to use the ideal gas law for both of those gases, I could just plug it in without it being so specific. So our van der Waals equation is oftentimes a more specific one. And again, we typically use this in our real gas situation, which basically means low temp or high pressure. So those are the sort of van der Waals situation or real gas situation. Any questions on that there? Obviously, if you needed it, those values would be provided for you and stuff like that. All right, that wraps up chapter 8, and it should be the last one that's on our exam, whenever our exam is, whatever day we ended up saying it, but this should be the last part of it. We will then continue on to chapter 9, I think. So give me 1 sec here to kind of get it up and running. Okay, so this should be chapter 9 here. We're going to talk a lot about liquids. We're also going to talk about phases and phase changes and all that good stuff. Let's move a couple of things out of my way here. Go that way, go that way. All right. And again, what we're talking about right now will not be on our next exam. So this should be on the following exam, if I'm not mistaken. So let's talk about this here, the liquid state. All right, so the first thing we're going to kind of talk about is intermolecular forces and sort of what they are and what they're responsible for and what properties of molecules that they really do affect. But I guess before we really kind of talk about intermolecular forces, we should really talk about, again, sort of the difference between an intermolecular force and an intramolecular force. So let's talk about that first. So let's start with an intramolecular force. An intramolecular force is basically the force that holds one individual molecule together. So it holds one molecule together. So again, if we look at something just like a single water molecule, the bond between the oxygen and the hydrogen on both sides, those are covalent bonds, and those would be intramolecular force, which means within a molecule. Ionic bonding as well is an intramolecular force. So ionic bonding, covalent bonding, these are intramolecular forces. And that is different than intermolecular forces. Intermolecular forces are the forces that basically hold one entire molecule together with another entire molecule. So if we took not just one water molecule, but 2 water molecules, water is a polar molecule, which means the oxygen side is more negative, hydrogen is more positive. And it is the negative side of one water which is attracted to the positive side of another water. And that is an intermolecular force. So an intermolecular force is that force that holds the one entire molecule together with another one. Now, they are definitely responsible intermolecular forces for things like boiling points, melting points, and as we'll see in the next little slide there, when we talk about the strength of the difference between them, the intramolecular force is always much stronger than the intermolecular force. So when we have this intermolecular force here, we know that it is much weaker than the intramolecular force because when we heat up something like water, for example, when we're boiling water, the first bond that breaks is actually this bond here, the bond between two individual water molecules. And what that will create is a water molecule that becomes a gas and another water molecule that becomes a gas. If it was opposite and the intramolecular force was actually weaker than the intermolecular force, what would happen when you start to heat this thing is these bonds would start to break, which would probably not be a good thing because you would start generating some hydrogen gas, some oxygen gas, and you probably would not get to the pasta making part of that adventure there. So we know that this doesn't really happen in that case. When we start to heat something like water, pretty simple example, we end up getting steam, which is basically different water molecules that basically occur. So the strongest sort of intermolecular force is really ionic bonding. It's a super strong intramolecular force. Again, covalent bonds, also a very strong one. But any type of intermolecular force is always going to be weaker than that intramolecular force. And again, it is responsible for, like I mentioned, things like boiling points and melting points. And that's because the stronger the intermolecular force, the more energy he has to put in there to get everybody to break apart from each other. The more energy he has to put in there, the higher things like the boiling point and melting points tend to be. So we're going to focus in on here in this chapter, really talking specifically about intermolecular forces. So we're going to talk about different types of intermolecular forces. And again, these are the forces that hold one entire molecule together with another. So the first type of intermolecular force is one that is referred to as a dipole-dipole force or dipole-dipole interaction. And all intermolecular forces, regardless of the different types we're going to talk about, pretty much all intermolecular forces are pretty much working the exact same way. So all these intermolecular forces really come down to a basic attraction of something that is positive and something that is negative, and that sort of electrostatic attraction, opposites attract, that basic attraction between something negative and something positive that holds it together. Where have we seen dipole before? Well, we've seen it before when we talked about bonding and polar molecules. So if you remember, if you have a polar molecule, it sometimes can be represented by that arrow, that dipole arrow. And if it is a polar molecule, it will have what is referred to as a dipole moment, right? Also represented by that arrow that we saw earlier. And ultimately, what that means is in a polar molecule, you essentially have one side of the molecule that is positive and one side that is negative. And because it's polar and it has a dipole moment, no matter what the situation is, it always has that positive side and negative side. There's nothing that could happen really to make it not be positive or negative. Negative is sort of a fixed positive side, negative side. So that builds up really well when we get a couple of polar molecules together. Positive side of one guy is attracted to the negative side of another. And now all these guys have a way to interact with each other. When they sort of come together, sort of in the solid phase, they do try to maximize the attractive forces and minimize the repulsive forces. So what that means is as they kind of come together in the solid phase, they keep kind of moving around, twisting and stuff like that until they could sort of maximize the areas where there's positive guys near negative guys and really try to minimize any positives near positives or negatives near negatives. No matter what you do, you probably will always have some positives near positives and negatives near negatives. But like I said, they'll kind of really continue to kind of move around until they find sort of a way that they're sort of can live with that sort of fact, and they have an overwhelmingly amount of positive and negative guys that are near each other. When we talk about dipole dipole interaction, this is the major force that holds together a polar molecule with another polar molecule. And what that means is it could be something that is polar attracted to itself. It could also be two different molecules that are attracted to each other, polar molecules, using dipole dipole interaction. And here's a prettier picture of what I was talking about. Again, as they do come together, they really do try to maximize areas where we get the positive and negative guys near each other and really minimize those places where we get, some positives and positives near each other and stuff like that. Another type of interaction that we see is one that is referred to as an ion dipole force. And it is pretty much like the name implies. An ion is a cation or an anion, right? So a cation, again, is a positively charged guy. Anion is obviously a negatively charged guy. And dipole means a polar molecule. So this is an attractive force between an ion and some type of polar molecule. This is basically what happens when we take something like sodium chloride and put it in water, right? When we put sodium chloride into water, it will break apart into sodium ions and chloride ions. And really what happens, right, is the sodium, which is positively charged, ends up getting surrounded by water's negative side, which in the case of water would be the oxygen. Water being our polar guy or our dipole, obviously sodium here being our ion, so our ion dipole interaction. Same thing with the chloride. Chloride is negative, so water will also surround it, but when it does, it's actually going to be the positive side of water, which is the hydrogen, that will end up surrounding the negatively charged ion. And that's essentially the interaction that occurs when we go to sort of dissolve something that's an ionic compound in something like water. And that's also what makes it dissolve, even though it looks to us like it's gone, it disappeared, it went away. It really didn't go away. It just got kind of mixed in with all the water, and we no longer can visually see it. But we do know it's still there because obviously, if you took this and you started heating it, what would happen is the water molecules would evaporate off, and then there would be nothing in between the sodium ion and the chloride ion from coming back together to make solid sodium chloride, which again, if you evaporate off all the water of a salt solution, you'll be left with a solid residue in whatever you have it in. And again, that's because you got rid of all those water molecules out of the way. They're able to come back together and make that solid reappear. So ion dipole interaction between an ion and a polar molecule. Again, that polar molecule has the fixed charge in terms of positive and negative, and it's able to interact really well with ionic compounds. Another type of intermolecular force is dispersion forces. And dispersion forces can come one of two ways or a few different ways. Um, dispersion forces are pretty weak type forces. So these are pretty much your weakest forces. And one way that we could kind of create a dispersion force is by creating what is sometimes referred to as an induced dipole. And an induced dipole is when we have something that normally does not have a charge, but temporarily sort of gains a charge. And it's a temporary gain of charge because electrons sort of move from one side of the molecule to another. We could do that by doing an ion-induced dipole interaction. So what that means is if I take my neutral guy and I put a positive ion next to it, just for the time being, in my neutral nonpolar atom, all the electrons here will decide, oh, I'm kind of attracted to the positive guy. And all the electrons in this guy will sort of head to the right-hand side. And now this guy that normally does not have a charge will gain this sort of temporary charge because its electrons sort of moved to the right-hand side of its molecule. And now it would be attracted, obviously, to that ion and have a way to basically interact with it through that positive negative attraction. Obviously, if the electrons head back the other way, the ion sort of moves around, it's going to break apart and not really be able to maintain that holding. Same thing happens if we put kind of a polar molecule next to it, and that's what's sometimes referred to as a dipole-induced dipole. Same idea if we slapped a polar molecule next to this guy that is normally nonpolar or neutral, and the negative side of our polar molecule was next to it, the electrons in our nonpolar guy would actually go away because it doesn't want to be near it. And again, what that's going to do is, as you can see down here, create a temporary positive charge in our nonpolar guy, and we will have an attractive force that can now happen between the positive side and the negative side. So these are kind of very weak type forces. They need somebody to sort of induce it or make it happen. And again, because they don't always have that separation of charge, as soon as those electrons find a need or want to kind of go back, it's going to kind of break apart. And another common way that this could actually sort of happen is what happens when we have really two nonpolar molecules near each other. So when we have two nonpolar molecules near each other, neither one has a charge. So if we don't put anything that's polar next to it or ionic next to it, it doesn't really have a way to have a charge. But it can actually make a charge temporarily. And this is what is known as an instantaneous dipole. So if we had two nonpolar guys, they have electrons there, and electrons are obviously moving around. And what could just happen just from those electrons moving around is all the electrons decide, say, in this first guy, we're all just going to go vacation over here on the left-hand side of the molecule. So what ends up happening in that case is that first molecule, which normally does not have a charge, will now gain a temporary charge on each side. And if it's still sitting next to the second nonpolar molecule, the electrons in this guy can go, oh, cool, there's like a positive guy. I'm going to go this way. And now our second nonpolar guy, which normally doesn't have a charge, will gain a temporary charge. And now we have a positive side of one and a negative side of the other, and it has a way basically to interact with each other. And that is what is known as an instantaneous dipole. The ability or ease at which that can happen is what is sometimes referred to as polarizability. So the greater the polarizability, there's a greater shot that those electrons will just sort of migrate to one side or the other. All three of these things are dispersion forces. They're all relatively weak type of interactions because essentially they rely upon something to happen and they cannot maintain it. And this is why, for example, when we take something that's polar and nonpolar and put it together, temporarily they can interact with each other, but over a long period of time, they have no sustained way to keep that interaction going on. Kind of like oil and vinegar salad dressing, right? You can mix it really well for a short period of time, right? Things are interacting, they're mixing. If you let it sit there over a long period of time, the oil and water sort of part of it is going to separate out from each other. They have no long range way of maintaining those connections, like we see, say, in something like dipole-dipole. So dispersion forces do increase with molecular mass. So if you have to choose between, say, two nonpolar guys and they're both going to be essentially using dispersion forces as their main source. The one that has the greater molar mass would have the stronger dispersion force, because the larger the molecule, again, there would be more electrons. More electrons would allow for more chance of those electrons moving around and creating that temporary positive and negative charge. When we talk about dispersion forces, it really is the major interaction that occurs between basically two nonpolar molecules. This is the basic way that nonpolar molecules and nonpolar molecules basically interact with each other. Um, in reality, everybody could do some type of dispersion force, but in terms of nonpolar, that is their main route of interaction between each other. Again, it is much weaker than dipole-dipole. Dipole-dipole is a much stronger uh, intermolecular force. Dipole-induced dipole, and dispersion forces, sometimes referred to as van der Waals forces, as we just saw with our gas law there. That's one of the things he thought about with gases, was sort of those interactions that basically occur between different molecules. And here's sort of a better picture. We have our instantaneous dipole. Again, normally does not have a charge. Makes the second guy also gain a charge where it normally doesn't have a charge. And now it has a way really to interact with each other through the negative side of one molecule and the positive side of another. The last type of intermolecular force is what is known as hydrogen bonding. And actually, hydrogen bonding is a type of dipole-dipole interaction. It's actually the strongest type of intermolecular force. So in terms of strength, there's hydrogen bonding, which is the strongest. Next is dipole-dipole. And the weakest out of all of them is our dispersion forces. So our dispersion forces is the weakest of all of the intermolecular forces. So what is hydrogen bonding? Hydrogen bonding is really happens when we have a hydrogen that is bonded to either nitrogen, oxygen, or fluorine. So if you look on the periodic table for those three, what you'll see is right about there, nitrogen, oxygen, fluorine. That is upper right of the periodic table. And what we know about electronegativity is that is the most electronegative right there at fluorine. So in order for something to have the ability to hydrogen bond, it has to be bound to those things. It has to actually be bound to a nitrogen, oxygen, and fluorine, because what that's going to do is create a polar bond between those things, right? So that's going to create a polar bond where the hydrogen and either the nitrogen, oxygen, or fluorine is obviously going to be more negative, right? This side will be more negative. This side will be more positive, is going to really create that separation of charge that occurs. So that is actually what happens with water. Water obviously has a hydrogen bonded to an oxygen. And again, oxygen being more negative, hydrogen being more positive. And that is, again, how these guys interact with each other through hydrogen bonding. Hydrogen bonding doesn't necessarily always have to occur between the same guys. You could have water, for example, and something like methanol here. Methanol also has this OH group, which is positive and negative. And again, these two different guys have the ability to hydrogen bond with each other. Now, something like NH3, NH3 can also hydrogen bond. It has a hydrogen that's attached to a nitrogen. It's polar, so it definitely has the ability to hydrogen bond as well. Now, what about CH4, for example? CH4, which looks something like this if we draw it. CH4 here has a lot of hydrogens, but it actually cannot hydrogen bond. So it cannot hydrogen bond. So why can it not hydrogen bond? Well, a couple of reasons. First off, our hydrogens here is not connected to a nitrogen, oxygen, or fluorine. Secondly, this whole molecule here is nonpolar, right? And the carbon hydrogen bond is nonpolar, so there's no separation of charge. There's no positive side or negative side. So this guy cannot hydrogen bond. We would expect CH4 to use dispersion forces because of that. So CH4 would use dispersion forces. Again, even though it has hydrogen, sometimes people make a mistake. They think that just because there's hydrogen there, that it definitely has the ability to hydrogen bond, and it doesn't. So it does have to be hydrogen, again, bonded to one of these guys. That's going to create really the polar bond that you need, that separation of charge that you need to be able to basically pull off hydrogen bonding. So, how does all these things sort of affect boiling points and melting points? Anything that has sort of the ability to hydrogen bond, we would expect the boiling point, the melting point to be relatively high. Anything that, is hanging out over here was kind of the dispersion aspect of it, it's going to have a relatively weak attraction, and we would expect it to be low boiling points and melting points to occur. Obviously, dipole-dipole somewhere in the middle. So, what is about dipole-dipole? What can actually happen with those guys? So, if we had something like, say, NF3, NF3 is polar, does not have any hydrogen, so it cannot hydrogen bond with itself. So, it would use something like dipole-dipole as its main sort of force. So ultimately, in terms of these three different types of intermolecular forces, hydrogen bonding is for polar molecules that have the ability to hydrogen bond. Dipole-dipoles for polar molecules that do not have the ability to hydrogen bond. And dispersion forces is really the main force that is used for nonpolar and nonpolar molecules interacting with each other. Any questions on that there? And that's what we see here. There's a whole bunch of hydrogen bonding happening here between our different water molecules and our ethanol and stuff like that. Again, between the hydrogen and our oxygen, that's basically occurring. Any questions on any of the intermolecular forces? Okay. So let's talk a little bit then about liquids. Obviously, liquids in the liquid state, everybody is still in there pretty tight to each other. There's a little bit more room for movement. They're able to sort of, move past each other, which is why liquids, right, are fluid. Um, they obviously are very hard to compress. You make kind of a mess if you try to compress a liquid. We talk about something about viscosity, which is really the resistance of a liquid to flow, and it is related to intermolecular forces. Again, sort of the stronger the intermolecular force, the less sort of flow you're going to have, right? Kind of weaker intermolecular forces, things will sort of flow a little bit better. So when we talk about water and some of its properties, two sort of properties that we sometimes see or talk about. One is cohesive forces, and that is the forces of attractions between molecules of a single substance. So water molecules with water molecules. Adhesive forces are those attractive forces between basically different molecules. And it's actually these two forces which basically result in when we put like a liquid, as we'll see in a later slide as well, a liquid in a glass container, we see that overly drawn meniscus occur, the curving of the water. And that's because, for example, the attractive forces between water and the surface, which would be sort of the adhesive forces, the glass in the container, is a lot stronger. So what ends up happening is the water starts to kind of ride up the sides of the container through sort of capillary action, and we get that curvature of the water. And it doesn't always happen with molecules. Sometimes the cohesive forces are stronger, as we'll see in a little later slide as well. And that's the case in like something like mercury. Mercury actually does a reverse sort of meniscus. And what that means is the mercury is attracted more so to the mercury itself, and it actually ends up going downward and creating that upwards curve that we see actually in something like mercury as well. And that would mean that the cohesive forces are stronger than the adhesive forces, and vice versa there when it curves the other way. Another sort of property of, say, water or something like that is what is referred to as surface tension. And surface tension is basically the elastic tendency of the surface to occur as the surface sort of expands. So when we think about sort of the surface of water, we have water molecules right there at the surface. And if we take, say, this water molecule at the surface, it's feeling attractive forces to the left, feeling attractive forces to the right and down. And what ends up happening is there's no attractive forces going upwards at the surface. So it ends up kind of stretching the surface, right? And creating tension as it kind of stretches out. And that's different than what we see if we're like in the middle of all those water molecules underneath the surface. If we had a bunch of water molecules and we look at this guy, he's sort of feeling attractive forces from sort of all directions, sort of equally. We don't get really that spreading out that occurs as well. Now, surface tension is usually higher in liquids with greater intermolecular forces. So something like hydrogen bonding, right? There's a really strong attractive forces pulling the surface, to each other and stuff like that, right? And you could kind of lay the paper clip on some water and it'll kind of sit there and stuff like that and not fall out. Um, Also, why certain bugs could walk on water, right? They can kind of walk on it. There's that surface tension of what's on the surface of it. You know, all those fun things like when we pour soda or liquid into our cup, right? And we go, cool, we're like way above the surface of it. And then we kind of shake our hand, break the surface tension, and then we make a mess. So basically, what happens here, if these are all sort of water molecules, as I mentioned, all those guys at the surface are going to feel the really strong hydrogen bonding, really going in sort of down into the sides, again, going to expand the surface of it and create a greater tension there. Then you feel below the surface, as I was mentioning, where there's a little bit more equal sort of pooling of those water molecules as well. So when we talk about something that can disrupt something like the surface tension of water and allow it to sort of spread out, we talk about something like soap. And soap, by the way, is basically two parts to soap. Soap has a part that basically is just nothing but carbons and hydrogens and really long chains of carbons and hydrogens all the way across. And this part of soap is what is referred to as being nonpolar. So this is like the nonpolar, sometimes referred to at tail of soap. And at the beginning part of it, I'll just go down. We have this sort of polar group that's here. So it has what is sometimes referred to as the polar head of soap. And that's what gives soap some properties that is good to use because basically a lot of dirt is nonpolar. So the nonpolar part of soap basically can surround dirt. Right? I'll just make the squiggly line the nonpolar part of soap. And when it does that, it traps all the dirt and what's referred to as a micelle. And on the outside is the polar part of soap. And when we usually use soap, we usually use water, which is polar. So the polar water, the polar part of soap mix really well and it washes the soap away, which the soap has all your dirt trapped in it and you feel clean. Good to know how soap works, I suppose, as well. But in addition, soap will also sort of get in between the hydrogen bonding that's occurring with water at the surface and really sort of spread out the water. So if you think about like your car when you water your car, yeah, in case you're bored and you're watering your car, when you hose it off maybe to wash it or it's raining. Usually, what we see, especially if your car is maybe waxed and stuff like that, right? We see a lot of the water would typically bead. You see all those beads that occur, and we have that non-polar sort of wax on it. Same thing with umbrellas. Typically, the water just sort of beads. And when we go to wash our car, we usually wet it down first, right? And we got all that water. And then we usually follow up with some soapy water, right? With the soap. And when you put the soap on, you can kind of see everything kind of spread out as you kind of do that. And what's happening again is the soap is getting in between sort of the water molecules and allowing things to spread out. Used to be that old Dawn soap commercial. They put a drop in and just sink with the dirt, and everything would just go and kind of spread out. I know, Google it, it'll be okay. But it gets in the way of that. It breaks out. It allows it to obviously kind of spread out and allow you to clean your car very well as well in there. So as I mentioned before, what we talked about just a second ago, we sometimes will see capillary action, which is when we have a glass tube with a very small diameter. Sometimes they're open on one side only, and you can actually use it. And this sort of attractive forces between sort of the liquid and the tube is actually enough to, kind of use just a small little tube, and you could actually start to kind of suck up some liquid in it as it would draw itself up into that tube. And again, what recurs with our adhesive forces versus our cohesive forces, again, if the attractive forces, like in a lot of liquids, to the glass is a lot stronger, we'll see our normal meniscus really start to occur here. But again, if the attractive force between, say, mercury and itself is much stronger, we'll actually see sort of that reverse meniscus basically start to occur. All right. Any questions on that? I think it's probably a good place to lay it up here for the week.